previous lesson, we have considered a quantum physical system which either consisted of only one particle or one qubit, or were prepared as a certain statistical ensemble, all the elements of which are in the same pure unmixed quantum state. The state vector of such system in the case of pure quantum states, or a set of state vectors in the case of a mixed state, were elements of a certain Hilbert space. In practice, it is often necessary to deal with several interacting quantum systems, or with a quantum system consisting of several subsystems. In particular, the implementations of quantum computing requires a physical system consisting of many qubits. In this case, we must consider the quantum state of such a system, taking into account the quantum state of each of its parts. And today, we'll learn how to do it. We'll firstly consider the pure states case. Suppose we have a physical system that consists of two qubits, that is, of two subsystems. In this case, the first qubit is described using the psi state vector, and the second is described by the phi state vector. The state vector of psi of the first qubit is an element of two-dimensional Hilbert space H1, and the state vector of phi of the second qubit is an element of the two-dimensional Hilbert space H2. Then the state of the whole system consisting of two qubits will be described by the tensor product of the vector psi and the vector phi, which is already an element of four-dimensional Hilbert space H, which is also obtained by the tensor product of the Hilbert spaces of the individual qubits H1 and H2. It should be noted here that it is important what kind of qubit we consider as the first and what as the second, because the order of tensor multiplying of the state vectors of these qubits, as well as the operators for which we act on them, depends on it. We now define a basis in the Hilbert space H of the entire system. Let for the first qubit a set of orthonormal state vectors psi1 and psi2 be a basis in the space H1. And for the second qubit, the set of orthonormal state vectors phi1 and phi2 is the basis in the space H2. Then, when the whole system consists of qubits 1 and 2, the basis will already consist not of 2, but of 4 state vectors, since the dimension of the space H will already be not 2, as it was for each qubit, but 4. This will be state vectors which are obtained by the tensor product of basis vectors of H1 and H2 spaces. That is, the vector psi1 is tensor multiplied by the vector phi1, the vector psi2 multiplied by the vector phi2, the vector psi2 multiplied by the vector phi1, and the vector psi2 multiplied by the vector phi2. Usually, to shorten this expression, such tensor products are written as one ket vector, but they are no longer designated by 1, just by 2 Greek letters with corresponding indices, as is done on the slide. Let's recall that in quantum mechanics, any characteristics of physical system, including observables, are expressed as linear operators, which we can write as matrices. In the case of single qubits, any operators that act on the state vector of such a qubit will be 2 by 2 matrices, and for a physical system consisting of 2 qubits, 4 by 4. At the same time, like the state vectors, they are also obtained by tensor products of operators acting on every qubit. Since the operation of the tensor product will be very important for us in the future, and in classical physics it is not so often can be founded, let us recall how it looks with a simple example. Let's consider it two simple examples for tensor product operation. First of all, we consider the tensor product of two vectors, the vector phi, which equals, for example, 1, 0, and vector psi, which equals 1, 1, multiplied by 1 divided by square root of 2. The tensor product of these two vectors is equals to 1 divided by square root of 2 0, 1, tensor multiplied by 1, 1. And we could rewrite this as following. 1 divided by square root of 2, 0 multiplied by vector 1, 1, 1 multiplied by a vector 1, 1. And finally, 1 divided by square root of 2, 0, 0, 1, 1. So, as you can see, if the vectors, the dimensions of initial vectors was 2, dimension of phi equals to 2, and dimension of psi equals to 2, the dimension of tensor product of phi and psi equals not 2, but 4. Secondly, we consider tensor product of two operators. So the first operator A, it, for example, equals to identity matrix 1, 0, 0, 1, and the operator B, which equals to 1, 1, 2, 2. So, the tensor product of two operators A and B equals to 1 multiplied by the matrix B, 0 multiplied by the matrix B, 0 multiplied also by matrix B, and 1 by the matrix B. So finally, we can obtain the following form of tensor product of two operators as the matrix 4 times 4, 1, 1, 0, 0, 2, 2, 0, 0, 0, 0, 1, 1, 0, 0, 2, 2. So, as you can see again, the dimension of operators was equals to 2, and the dimension of tensor product is equals to 4. We consider the operation of a tensor product when both operators and vectors belong to two different Hilbert spaces of dimension 2. Note that the tensor product can also be carried out in the case when the dimensions of the spaces do not coincide. On the slide that you see, the operator S is the matrix M by M, that is, it acts on the state vectors which are elements of a Hilbert space of dimension M. And the operator T is already the matrix N by N, that it refers to the Hilbert space of dimension N. As a result of the tensor product, as in our example, we obtain a block matrix of dimension M multiplied by N. A similar situation will be for state vectors. We emphasize that for each qubit, any operator will act on the Hilbert space of this qubit and will in no way act on other qubits. Thus, if we have the product of operators A1, A2, and A3, which act on one qubit, and the product of operators B1, B2, which act on another qubit, before performing the operation of the tandem product, we must first find the explicit form of the operators acting on every qubit. That is, first calculate the usual product of matrices A1, A2, and A3, then calculate the usual product of matrices by B1 and B2, and then find the tandem product of the obtained result to find the explicit form of the operator that acts on the state vector of the whole system. In addition, the operation of a tensor product has several important properties. Firstly, it is associative. That is, if we need to successfully multiply the tensor operators M, N, and L, first we can multiply tensor M by N and then multiply the result by L. Or we can multiply N by tensor M and multiply M by the tensor result, as is shown on the slide. Secondly, the operation of the tensor product is anti-commutative. That is, if we swap the multipliers, we get different results. Each of these properties is easily verified if you present each of these operators as their matrix form, so make sure of it by yourself. In conclusion, let us consider pure and mixed states of physical system consisting of several qubits, and introduce the definition for the so-called entangled states, which are a very important class of quantum states. Let's start with pure state. It is enough for us to consider a physical system consisting of two qubits. And as we know, the basis of such a system is expressed in terms of tensor products of the basic states of each qubit. On the slide, this is a set of psi I states multiplied by phi j states, where the indices I and j run through the values 1 and 2. Accordingly, any zeta state vector for the entire system can be represented as a decomposition by this basic set, that is, in the form of two sums of indices I and j from the coefficient c sub ij multiplied by the vector psi I tensor multiplied by the vector phi j. If the coefficients of these decompositions can be chosen so that the state vector of the whole system zeta can be represented not as a sum but as a tensor product of the state vectors zeta1 and zeta2, each of which refers to a separate qubit, that is, it is an element of a Hilbert space of this qubit, then such a state of a physical system consisted of two qubits is called separable. If this cannot be done, then the state of the system is called inseparable or entangled. A similar definition can be given for mixed states, which you can now see on the slide. This type of density matrix of the entire system, in the case of the separable states, follows from the definition of separable pure states that we have just formulated. Let's recall that the density matrix can be used not only to describe mixed states, but also to describe pure states, and in this case, it will simply correspond to the projector for this state. If a mixture of pure states consists of many components, that the density matrix will be equal to the sum of the projector for each such state, taken with the appropriate probability. Thus, if each projector is projected onto a separable state, then the entire density matrix, that is, the sum of such projectors, will describe the separable state of the entire system. Otherwise, the states of the physical system will be inseparable or entangled. That's all for now. Thanks for your attention.